In 1935, the world of physics was still reeling from the strange new rules of quantum mechanics. It was a theory that worked beautifully on paper, predicting the behavior of atoms with stunning accuracy. But it was deeply unsettling. That year, Albert Einstein, along with his younger colleagues Boris Podolsky and Nathan Rosen, published a paper. It was titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" The paper described a thought experiment, later known as the EPR paradox. It went something like this. Imagine two particles are created together. They are linked, entangled, they fly apart in opposite directions. Quantum mechanics says that until you measure a property of one particle, like its position or momentum, its state is uncertain. It exists in a haze of probabilities. But the moment you measure one particle, you instantly know the state of the other. Instantly. It doesn't matter if it's across the room or across the galaxy. This connection, this spooky action at a distance, as Einstein called it, seemed to break the cosmic speed limit, the speed of light. Information appeared to travel faster than light. For Einstein, this was a clear sign that quantum mechanics was incomplete. There had to be hidden variables, some local information the particles carried with them from the start. Reality, he believed, was not so probabilistic and weird. He spent the rest of his life trying to find a more complete theory, a unified field theory that would connect his own theory of gravity, general relativity, with the other forces of nature. He never found it. It turns out Einstein was wrong about entanglement. Experiments starting in the 1970s and 1980s, most notably by John Clauser and Alain Aspect, prove that this spooky connection is real. The quantum mechanics is just that strange, but his quest touched on the deepest problem in modern physics, a problem that remains unsolved today. The universe seems to operate under two completely different sets of rules. There's the wild, uncertain world of quantum mechanics that governs the very small, and there's the smooth, deterministic world of general relativity that governs the very large, the world of planets, stars, and galaxies held together by gravity. These two theories are the twin pillars of modern physics. They are also completely incompatible. When you try to use them together in places where the very small meets the very massive, like in the center of a black hole or at the moment of the Big Bang, the math breaks down. Or it gives you nonsense answers like infinities. This clash between our best theory of the large and our best theory of the small is the great unresolved crisis in science. And at the heart of that crisis is gravity. It's the one force that refuses to fit into the quantum world. Well, we understand so much, yet we understand so little about this force that shapes the cosmos. It's the architect of the universe, and we are still strangers to its true nature. Number 19, gravity is weirdly, impossibly weak. A small refrigerator magnet can lift a paperclip, defying the gravitational pull of the entire planet Earth. Gravity is roughly a trillion times weaker than the electromagnetic force that holds that magnet together. If you were to drop two protons, the electrical repulsion between them would be about 10 raised to the power of 36 times stronger than their gravitational attraction. This isn't just a small difference. It is the single largest and most baffling disparity in all of physics. This is known as the hierarchy problem. It's the question of why there is such a colossal gap between the strength of gravity and the other three fundamental forces of nature, the strong nuclear force, the weak nuclear force, and electromagnetism. These other forces operate in a relatively cozy range of strengths. But gravity is the outcast, so feeble it's almost a rounding error in the particle world. At the subatomic level, gravity is so insignificant that physicists usually ignore it completely in their calculations. And yet, on the scale of the cosmos, it is the undisputed master. It is the force that pulls gas clouds together to form stars, that holds planets in orbit, and that clusters galaxies into immense superstructures. This weakness is not an accident. It is essential for our existence. If gravity were even a little bit stronger, the universe would be a very different place. The stars would burn through their fuel much faster, possibly too fast, for life to evolve on any orbiting planets. A star like our sun, which has a lifespan of about 10 billion years, might last only a few million. If gravity were as strong as the other forces, the universe would have likely collapsed back in on itself a fraction of a second after the Big Bang. There would be no atoms, no stars, no us. The universe would be a sea of tiny black holes. So why is it so weak? Nobody knows for sure, but there are some compelling ideas. One of the most popular comes from string theory. The idea is that our universe, with its 3 dimensions of space and 1 of time, is just a sliver of a much larger, higher dimensional reality. We might be living on a 3-dimensional brain embedded in a larger space called the bulk. The particles and forces of the standard model, like electrons and photons, are stuck to our brain. They can't leave it. But gravity, according to this theory, is different. Gravity is a property of space-time itself, so it is not confined to our brain. The particle associated with gravity, the hypothetical graviton, can travel freely through all the extra dimensions. This would mean that gravity isn't actually weak. We just experience a tiny fraction of its true strength, because most of it is leaking away into these other dimensions we can't see. To test this, scientists at the Large Hadron Collider LHC smash particles together at incredible energies. If these extra dimensions are real and accessible, these collisions could create tiny, short-lived black holes or produce gravitons that fly off into the bulk, carrying energy with them. So far, no such evidence has been found. Another idea involves something called supersymmetry. This theory proposes that every known particle has a superpartner with slightly different properties. These superpartners would have canceled out certain quantum effects in the very early universe that would have otherwise made gravity much stronger. It's an elegant mathematical solution, but like the extra dimensions, searches at the LHC have so far failed to find any of these supersymmetric particles. A third possibility is that gravity isn't a fundamental force at all. Maybe it's an emergent phenomenon, something like temperature or pressure. You can't talk about the temperature of a single atom. Temperature is a property that emerges from the average motion of many atoms. In the same way, perhaps gravity isn't a basic property of reality, but an emergent effect arising from the complex quantum interactions of other, more fundamental fields. This is a radical idea, and the math is still in its infancy, but it represents a different way of thinking about the problem. The hierarchy problem remains one of the biggest motivators for research in theoretical physics. It's a giant loose thread in our understanding of the universe. Pulling on it could unravel everything we think we know. Number 18, gravity's quantum particle is missing. The graviton has never been detected. In fact, it might be impossible to ever detect a single one. To find a single graviton using a detector the size of Jupiter placed in orbit around a neutron star, you would have to wait longer than the current age of the universe. The physicists are that certain it exists and that certain will never see it. Every other fundamental force has a carrier particle. Electromagnetism is carried by the photon, the particle of light. The strong nuclear force which binds atomic nuclei together is carried by the gluon. The weak nuclear force responsible for radioactive decay is mediated by W and Z bosons. All of these particles have been discovered and studied extensively. They are the bedrock of the standard model of particle physics, our incredibly successful theory of the subatomic world. The standard model works perfectly, but it has a gaping hole. There is no quantum particle for gravity. The hypothetical carrier particle for the gravitational force is the graviton. According to quantum field theory, forces work by exchanging these carrier particles. When 2 electrons repel each other, they are actually exchanging photons. So when the Earth pulls on the moon, they should, in theory, be exchanging gravitons. The problem is that gravity is so astonishingly weak. The interactions are so infrequent and so feeble that detecting a single graviton is likely beyond our technological reach, possibly forever. This puts physicists in a strange position. They need the graviton to exist for their theories to make sense. A quantum theory of gravity, the long-sought theory of everything, absolutely requires a graviton. It would have to be a particle with no mass and no charge, and it would travel at the speed of light. It would also have a property called spin 2. All other force carriers have spin 1. This difference is crucial and comes directly from the mathematics of general relativity. Einstein's theory describes gravity as a distortion of spacetime, a fabric that is distorted by mass and energy. A spin 2 particle is the only kind that can create the type of interaction that mimics this distortion. So, if we can't detect a graviton directly, can we find indirect evidence? One of the best hopes is gravitational waves. These ripples in spacetime, first predicted by Einstein in 1916 and first detected by the LIGO experiment in 2015, are like giant waves of countless gravitons all moving together. Detecting the wave is one thing, but seeing the individual quanta or particles that make up the wave is another. It's like seeing the wave on the ocean, but trying to isolate a single water molecule within it. Another place to look is the very early universe. The cosmic microwave background CMB is the leftover heat from the Big Bang. It's a faint glow of radiation that fills the entire sky. Tiny temperature fluctuations in the CMB are the seeds of all the galaxies and structures we see today. Physicists believe that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called inflation. This process would have created a background of gravitational waves, a storm of primordial gravitons. These gravitational waves would have left a specific twisting or curling pattern in the polarization of the CMB light, known as B-mode polarization. In 2014, a team of scientists at the South Pole thought they had found this signal. The announcement made headlines around the world. It seemed to be the smoking gun for inflation and indirect evidence of quantum gravity. But later analysis showed that the signal was actually caused by cosmic dust within our own galaxy. The search continues, with more sensitive telescopes being built to hunt for this faint, ancient signal. The missing graviton is more than just a missing particle. It represents the chasm between our two best theories of the universe. Without a working theory of quantum gravity, we can't understand what happens in the most extreme environments, like the center of a black hole or the moment of creation. The graviton is the key. Finding it, or proving it doesn't exist, would change physics forever. For now, it remains a ghost in the machine. Number 17, we don't know how fast gravity travels. On August 17th, 2017, two neutron stars spiraled into each other and merged 130 million light-years away from Earth. The collision sent out a burst of gravitational waves, which were detected by the LIGO and Virgo observatories. Just 1.7 seconds later, space telescopes detected a flash of gamma rays from the same spot in the sky. This event was monumental. It marked the first time we had ever observed both gravitational waves and light from the same cosmic event. This observation allowed physicists to perform an incredible test. The gravitational waves and the light traveled for 130 million years to reach us. They arrived at almost the exact same time. The tiny 1.7-second delay is easily explained by the complex physics of the merger itself. The gamma rays were likely emitted just after the initial collision. This meant that gravity travels at the speed of light, to an accuracy of about 1 part in a quadrillion 10 raised to the power of 15. This was a stunning confirmation of a key prediction of Einstein's general theory of relativity. But the story isn't quite that simple. While this measurement was a landmark achievement, it only tells us about the speed of gravitational waves. The deeper question is about the speed of gravity itself in its static, everyday form. What is the speed of the gravitational field? This might sound like the same question, but there's a subtle and important difference. Imagine the sun suddenly vanished. How long would it take for the Earth to fly off into space? According to general relativity, the information that the sun is gone would travel outward as a gravitational wave. So we would continue to orbit the sun's empty location for about 8.3 minutes, the time it takes for light and gravitational waves to travel from the sun to the Earth. This seems straightforward, but some physicists have pointed out that the situation is more complex. Gravitational fields aren't just about waves, they are also about the constant pull we feel. Some alternative theories of gravity have proposed that the speed of the static field could be different from the speed of the waves. This is especially relevant when trying to explain things like dark matter. Some theories that try to get rid of dark matter by modifying the laws of gravity known as MOND or modified Newtonian dynamics run into trouble with the speed of gravity. If gravity's influence propagates at a different speed, it would change the way galaxies rotate and bend light in ways that don't match our observations. The 2017 neutron star merger known as GW170817 dealt a severe blow to many of these alternative theories. By showing that gravitational waves travel at the speed of light, it ruled out a large class of models that required gravity to travel at a different speed. However, the question isn't completely closed. We have only made this measurement for one specific type of event. Physicists want to make more measurements from different sources to be absolutely sure. There's also the quantum question. If gravity is quantized and has a particle, the graviton, then that particle must be massless. Any particle with mass must travel slower than the speed of light. So confirming that gravity travels at the speed of light is also a way of confirming that the graviton, if it exists, has zero mass. Even a tiny, tiny mass would cause gravitational waves of different frequencies to travel at slightly different speeds. Over millions of light years, this would cause the signal to spread out and disperse. The sharp signal we received from GW78181 puts a very tight limit on the possible mass of the graviton, making it at least 10 raised to the power of 22 times lighter than an electron. So, we are very confident that gravity travels at the speed of light. But physics is a science of precision and skepticism. We have measured it once with incredible accuracy. Now, scientists want to measure it again and again, pushing the limits of what we know. Because in the small uncertainties and the tiny deviations from what we expect, a new revolution in physics might be waiting. Number 16, the universe's expansion is accelerating and we don't know why. In the late 1990s, two separate teams of astronomers were doing what seemed like a routine job. They were using distant supernovae, the explosive deaths of massive stars, as standard candles to measure the expansion rate of the universe. Everyone knew the universe was expanding, that had been established since the 1920s by Edwin Hubble. And everyone assumed that the expansion was slowing down. Gravity, after all, pulls things together. The combined gravity of all the matter in the universe should be acting as a brake on the expansion, causing it to decelerate over time. The only question was by how much. Would it slow down and stop, reverse, and end in a big crunch? Or would it slow down but continue expanding forever? In 1998, both teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Riess, came to a shocking conclusion. The distant supernovae they were observing were dimmer, and therefore farther away than they should have been. The only way to explain this was if the expansion of the universe was not slowing down. It was speeding up. This was a discovery that turned cosmology on its head. It was like throwing a ball into the air and watching it accelerate up into the sky instead of falling back down. You know, there had to be some kind of mysterious, repulsive force pushing the universe apart. This mysterious force was given a name, dark energy. It is the most dominant thing in the universe. It makes up about 68% of the total energy density of the cosmos. Dark matter makes up about 27%. All the ordinary matter, everything we can see, all the stars, galaxies, planets, and people, accounts for less than 5%. We are a tiny bit of froth on a vast, dark ocean. The discovery of dark energy earned Perlmutter, Schmidt, and Riess the Nobel Prize in Physics in 2011. But giving it a name didn't mean we understood it. We still have almost no idea what it is. The leading candidate for dark energy is something called the cosmological constant. This was an idea that Albert Einstein had back in 1917. When he first formulated his theory of general relativity, his equations told him the universe should be either expanding or contracting. But the prevailing view at the time was that the universe was static and eternal. To fix this, he added an extra term to his equations, a kind of fudge factor that would act as a repulsive force to balance out gravity and keep the universe stable. He called it the cosmological constant. When Hubble discovered the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder. But with the discovery of accelerating expansion, it seems his blunder might have been right all along. The problem is, when we try to calculate how strong this cosmological constant should be based on our understanding of quantum physics, we get a spectacular failure. Quantum mechanics predicts that empty space is not empty at all. It's a bubbling, seething foam of virtual particles popping in and out of existence. This activity has energy called vacuum energy. This vacuum energy would act exactly like a cosmological constant. But when physicists calculate the expected value of this vacuum energy, the result is about 10 raised to the power of 120 times larger than the value we observe. This is the single worst theoretical prediction in the history of physics. It's an error so large that it's difficult to even write out the number. So, if it's not the cosmological constant, what else could it be? Perhaps it's a new kind of energy field, a fifth essence called quintessence, that permeates all of space and changes over time. Unlike the cosmological constant, which is constant, quintessence could have different strengths at different times in the universe's history. Or maybe, and this is the most radical idea, Einstein's theory of gravity is wrong on cosmological scales. Perhaps there is no dark energy, and the acceleration we observe is a sign that we need a new theory of gravity. To figure this out, astronomers are building new telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope. They will map the universe in unprecedented detail, tracking millions of supernovae and galaxies to get a precise history of the cosmic expansion. By seeing how the acceleration has changed over time, they hope to distinguish between the different theories. Is dark energy constant, or does it evolve? The answer will determine the ultimate fate of our universe. Will it expand forever, tearing everything apart in a big rip, or will the dark energy weaken, allowing gravity to take over again? We live in a runaway universe, and we are still trying to understand the engine that's driving it. Number 15, we can't find 85% of the matter in the universe. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies. He was measuring the speeds of the individual galaxies as they orbited the cluster's center of mass. What he found was deeply puzzling. The galaxies were moving so fast that the gravity from all the visible matter in the cluster, all the stars and gas he could see, was not nearly strong enough to hold them in their orbits. The cluster should have flown apart millions of years ago. To explain this, Zwicky proposed that there must be a huge amount of unseen matter, which he called Dunkel Materie, or dark matter. His calculations suggested there was hundreds of times more dark matter than visible matter. His idea was largely ignored for decades. Then, in the 1970s, an American astronomer named Vera Rubin was studying the rotation of spiral galaxies, including our neighbor Andromeda. She expected to see stars at the edge of the galaxy rotating more slowly than stars near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. This is basic Newtonian gravity, but that's not what she found. The stars on the outer edges were moving just as fast as the stars in the middle. The only way to explain this was if the galaxies were embedded in a massive, invisible halo of dark matter, extending far beyond the visible stars. Her precise observations provided the first robust evidence that Zwicky had been right all along. Today, the evidence for dark matter is overwhelming. We see its gravitational effects everywhere we look. We see it in the way galaxy clusters bend the light from more distant objects, a phenomenon called gravitational lensing. The amount of bending tells us how much mass is there, and it's far more than we can see. We see its imprint in the cosmic microwave background, the afterglow of the Big Bang. The specific pattern of hot and cold spots in the CMB can only be explained if the universe contains a large amount of non-luminous, non-reacting matter. From all these different lines of evidence, a consistent picture has emerged. About 85% of all the matter in the universe is dark matter. So, what is it? That is the billion-dollar question. We know what it's not. It's not just dark clouds of normal matter, because we would be able to detect them from the radiation they absorb or emit. It's not black holes or neutron stars, because we would see their gravitational effects on nearby stars. You know, it has to be something completely new, a new kind of particle that is not part of the standard model of particle physics. The leading candidates are called WIMPs, or weakly interacting massive particles. These are hypothetical particles that are very heavy, massive, and interact with normal matter only through the weak nuclear force and gravity weakly interacting. This would explain why we haven't seen them. They would pass through us, through the Earth, through everything, almost as if it weren't there. Scientists are trying to detect WIMPs in 3 ways. The first is to build ultra-sensitive detectors deep underground, shielded from cosmic rays, and wait for the tiny flash of light or vibration that would be produced if a WIMP happened to bump into an atomic nucleus. There's experiments like LUX, Zeppelin, LZ in South Dakota, and Xenont in Italy are doing just this. So far they have found nothing. The second way is to try to create dark matter particles in accelerators like the Large Hadron Collider. If WIMPs exist, they might be produced in high-energy proton collisions. We wouldn't see the WIMPs themselves, but they would carry away energy and momentum, leaving a telltale signature of missing energy in the detector. Searches for this signature have also come up empty. The third method is to look for signs of dark matter annihilating itself out in space. If 2 WMPs meet, they should annihilate and produce a shower of familiar particles like gamma rays or neutrinos. And telescopes like the Fermi Gamma Ray Space Telescope are scanning the skies, especially the dense center of our galaxy, where dark matter should be concentrated, looking for this excess of high-energy radiation. Some tantalizing hints have been seen, but nothing conclusive. The persistent failure to find WIMPs has led some physicists to consider other possibilities. Maybe dark matter is made of a much lighter particle called an axion, or perhaps it's a sterile neutrino, a heavier cousin of the familiar neutrino. Or maybe, and this is the most controversial idea, there is no dark matter at all. Perhaps our theory of gravity is wrong. This idea, called modified Newtonian dynamics MOND, suggests that gravity behaves differently on galactic scales than it does in our solar system. MOND can explain the rotation of galaxies remarkably well without invoking dark matter. However, it struggles to explain the observations of galaxy clusters and the cosmic microwave background. For now, the hunt for the missing matter of the universe continues, one of the greatest detective stories in the history of science. Number 14, is gravity a fundamental force at all? Or gravity might not be fundamental, it could be an illusion. This is a radical idea, but it's one that a growing number of theoretical physicists are taking seriously. For centuries, we have thought of gravity as one of the basic irreducible forces of nature, like electromagnetism. But what if it's not? What if gravity is an emergent phenomenon, a side effect of something deeper happening at the quantum level? Think about temperature. We experience temperature as a fundamental property of the world. We feel hot and cold, but we know from physics that temperature isn't fundamental. It's an emergent property of the average motion of atoms and molecules. A single atom doesn't have a temperature. And temperature only makes sense when you have a large collection of particles. The same goes for pressure in a gas or the fluidity of water. These are all emergent properties that arise from the collective behavior of microscopic components. The idea of emergent gravity, sometimes called thermodynamic gravity, proposes that gravity works in a similar way. In 2010, the physicist Eric Verlinde published a paper arguing that gravity is not a fundamental force, but an entropic force. Entropy is a measure of disorder or information in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Verlinde's idea connects this fundamental law of thermodynamics to the laws of gravity. He suggested that when an object moves, it changes the amount of information associated with the space around it. The universe, behaving like a thermodynamic system, resists this change, creating a force. That force, he argued, is what we perceive as gravity. In this view, gravity is simply a manifestation of the universe's tendency to maximize disorder. This idea is closely related to the holographic principle, which came from the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This was a startling result. It suggested that all the information about what fell into the black hole is somehow encoded on its two-dimensional surface. This led to the idea that our entire three-dimensional universe might be a projection, a hologram of information stored on a distant two-dimensional boundary. If the holographic principle is true, then gravity in our 3D universe could be an emergent consequence of quantum interactions happening on that 2D surface. The fundamental reality would be a quantum field theory without gravity, living on the boundary of spacetime. The spacetime we inhabit and the force of gravity that governs it would be the holographic projection. This isn't just a philosophical idea. There is a precise mathematical dictionary called the ADS-CFT correspondence that links a specific type of gravitational theory in a higher dimensional space, the bulk, to a quantum field theory without gravity in a lower dimensional space, the boundary. This correspondence has become one of the most powerful tools in theoretical physics. What would it mean if gravity is emergent? For one, it could solve the problem of quantum gravity. If gravity isn't a fundamental quantum force, then we don't need to quantize it. We don't need a graviton. The problem of unifying gravity with the other forces would disappear, because gravity would be in a different category altogether. It would also offer a new perspective on dark matter and dark energy. Some proponents of emergent gravity suggest that these mysterious phenomena might be explained as thermodynamic effects related to the information content of the universe. However, the theory of emergent gravity is still highly speculative and faces many challenges. It's not yet a complete theory. It struggles to reproduce all the successes of Einstein's general relativity, especially in strong gravitational fields. And it's not clear how to test it experimentally, but it represents a profound shift in how we think about the nature of reality. It suggests that space-time and gravity are not the fundamental bedrock of the universe. They are part of the emergent macroscopic world, like the wetness of water. The truly fundamental reality may be a strange, timeless, and spaceless world of pure quantum information. Number 13. What is the true nature of space-time? At the heart of Einstein's theory of general relativity is the concept of space-time. It is a four-dimensional fabric weaving together the three dimensions of space and the one dimension of time. Mass and energy tell this fabric how to curve, and the curvature of the fabric tells mass and energy how to move. This is a beautiful and powerful idea that has been confirmed by countless experiments. But what is this fabric made of? Is space-time a smooth, continuous sheet, as Einstein imagined it? Or, if you could zoom in to the smallest possible scales, would you find that it is made of tiny, discrete units, like a digital image is made of pixels? This is the question of whether space-time is continuous or quantized. Our two great theories of physics give different answers. General relativity assumes space-time is smooth and continuous. Quantum mechanics, on the other hand, suggests that everything is ultimately discrete. Energy comes in packets called quanta, forces are carried by particles. It seems natural to assume that space and time themselves should also be quantized at some fundamental level. This fundamental unit of space would be incredibly small. The smallest possible distance is thought to be the Planck length, which is about 1.6 × 10 raised to the power of 35 meters. To give you a sense of how small that is, if you were to scale up an atom to the size of the observable universe, the Planck length would be about the height of a tree. The smallest unit of time would be the Planck time, about 10 raised to the power of 43 seconds, which is the time it takes for light to travel 1 Planck length. Probing these scales is far beyond the reach of any conceivable experiment, so how can we find out? Theorists have developed several approaches to quantum gravity that predict a quantized spacetime. One of the leading contenders is called loop quantum gravity LQG. This theory proposes that the fabric of spacetime is not a smooth sheet, but a network of interconnected loops. These loops are the fundamental quanta of space. You can't have half a loop. The volume of space is built up from these discrete units. The area of a surface is determined by the number of loops that pierce it. In this picture, spacetime is a dynamic, evolving network of relationships. It's not a background stage on which the play of the universe unfolds, it is the play. String theory, another major approach to quantum gravity, also hints at a non-continuous nature of space. While it starts with strings moving in a smooth background spacetime, more advanced versions of the theory, like M-theory, suggest that spacetime itself is an emergent concept that breaks down at the Planck scale. Another idea is causal set theory, which proposes that spacetime is fundamentally a collection of discrete points, and the only thing that is real is the causal relationship between them, which events caused which other events. The geometry of spacetime emerges from this underlying causal network. Finding evidence for a quantized spacetime is extremely difficult, but not impossible. One idea is to look for tiny variations in the speed of light. If spacetime is a discrete grid, then high-energy photons, light particles, might travel slightly differently through it than low-energy photons. The effect would be minuscule, but over billions of light years of travel from a distant cosmic explosion like a gamma ray burst, this tiny difference could add up. Where telescopes like the Fermi Gamma Ray Space Telescope are looking for this effect by carefully timing the arrival of photons of different energies from the same burst. So far, no such variation has been found, which puts tight constraints on some models of quantum spacetime. Another possibility is to look for quantum foam. At the Planck scale, the uncertainty principle of quantum mechanics would cause spacetime itself to fluctuate wildly. Tiny wormholes and bubbles of spacetime would be constantly popping in and out of existence. This foaminess might leave a subtle imprint on the light from distant quasars, causing their images to appear slightly blurry. Astronomers are using the most powerful telescopes to look for this effect, but again, the results have been negative so far. The nature of spacetime is one of the deepest questions in all of science. Is the universe analog or digital? Is the fabric of reality smooth or chunky? The answer will not come easily, but it will fundamentally change our understanding of what space, time, and gravity truly are. Number 12, does gravity behave the same on all scales? We assume that the law of gravity is universal. The same force that makes an apple fall to the ground also holds the moon in orbit and binds galaxies together. This principle of universality is a cornerstone of physics, but is it actually true? Sure, we have tested Newton's and Einstein's laws of gravity with incredible precision in our solar system, but we have surprisingly few direct tests of gravity at very small scales or at very large cosmological scales. It's possible that gravity behaves differently in these extreme regimes. Let's start with the very small. We have never measured the gravitational force between two objects at distances smaller than about 50 microns, the width of a human hair. It's an incredibly difficult experiment to do because gravity is so weak, and at these small distances, other forces like the electrostatic Casimir effect become dominant. Why would gravity change at small scales? One reason could be the existence of extra dimensions. As we discussed with the hierarchy problem, some theories suggest that gravity is the only force that can travel in these extra dimensions. At our everyday scales, these dimensions would be curled up so tightly that we don't notice them. But as you get very close to an object, you might start to feel the effects of gravity in these extra dimensions, causing it to become much stronger than predicted by the inverse square law. In experiments using tiny, oscillating cantilevers or trying to probe gravity at these sub-millimeter scales, looking for any deviation from Newton's law. So far they have found none. Now let's consider the very large. Our entire model of cosmology is built on the assumption that general relativity is the correct theory of gravity on the scale of galaxies and the entire universe. This assumption has led us to the conclusion that the universe is filled with dark matter and dark energy. But what if the assumption is wrong? What if the strange behavior we attribute to these dark components is actually a sign that gravity itself is changing on these vast scales? This is the idea behind modified Newtonian dynamics, or MOND, proposed by the physicist Mordechai Milgrom in 1983. MOND suggests that Newton's law of gravity is correct in high acceleration environments like our solar system. But in very low acceleration environments like the outer edges of galaxies, gravity is actually stronger than Newton predicted. This modification is very specific. Below a certain critical acceleration, the gravitational force becomes proportional to the acceleration itself, not the acceleration squared. This simple change can explain the flat rotation curves of spiral galaxies with stunning accuracy without any need for dark matter. For a long time, MOND was considered a fringe idea, but it has had some remarkable successes. It not only explains galaxy rotation curves, but it has also successfully predicted the properties of galaxies before they were measured. However, MOND has its own problems. In its original form, it struggles to explain the dynamics of galaxy clusters, where we still seem to need some form of dark matter, though much less than in the standard model. It also has a hard time explaining the pattern of fluctuations in the cosmic microwave background. And as a theory, it is not as elegant as general relativity. It is an ad hoc modification, not a fundamental theory derived from first principles. And efforts have been made to create a relativistic MOND, a theory that modifies general relativity itself. These theories are complex, and many have been ruled out by observations like the neutron star merger GW 17817, which showed that gravity travels at the speed of light. Still, the idea that gravity might be different on large scales remains a tantalizing possibility. The question of whether gravity is truly universal is a fundamental one. Is the law of gravity the same in the lab, in the outer reaches of a galaxy, and in the universe as a whole? Or does it change its character depending on the scale? Future observations from telescopes like the Euclid Satellite and the Vera Rubin Observatory will map the distribution of matter and the expansion of the universe with unprecedented precision. These maps will provide the most stringent tests yet of general relativity on cosmological scales. They will either confirm Einstein's theory once again, or they will reveal the cracks in our understanding of gravity, pointing the way to a new, more complete theory. Number 11. What is inside a black hole? According to general relativity, at the center of every black hole lies a singularity. It is a point of zero volume and infinite density, where all the matter that has fallen into the black hole is crushed out of existence. At the singularity, the curvature of space-time becomes infinite, and the laws of physics as we know them break down. It is a place where our two best theories of the universe, general relativity and quantum mechanics, collide and fail. But does such a thing as a physical infinity actually exist in nature? Many physicists think not. The singularity is not a real object, they argue, but a sign that our theory is incomplete. It's a placeholder for a new theory of quantum gravity that we have yet to discover. This new theory would tell us what really happens to matter at the center of a black hole. So, what are the possibilities? One idea comes from loop quantum gravity. In this theory, space-time is made of discrete quantum loops. There is a minimum possible size. This means that matter cannot be crushed to an infinitely small point. Instead, as matter collapses under gravity, it would reach a state of maximum density, a Planck star. At this point, quantum pressure would resist the pull of gravity, causing the matter to rebound in a Planck bounce. From the outside, it would still look like a black hole, but instead of a singularity, the center would contain this incredibly dense, bouncing core. Some have even speculated that this bounce could lead to the creation of a new baby universe inside the black hole. String theory offers another perspective. It suggests that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. From this viewpoint, a black hole might not be a singularity, but a fuzzball. A fuzzball has no singularity and no event horizon in the classical sense. Instead, the black hole is a tangled ball of strings with a definite size. All the information about the matter that fell in is preserved in the vibrations of these strings. From a distance, a fuzzball would look and act exactly like a classical black hole. But up close, it would be a solid, albeit exotic, object. There's also the question of the event horizon, the point of no return surrounding a black hole. According to classical physics, nothing, not even light, can escape from once it has crossed the event horizon. But in the 1970s, Stephen Hawking showed that when you include quantum effects, black holes are not completely black. They should slowly emit thermal radiation, now known as Hawking radiation. This radiation is caused by quantum fluctuations near the event horizon. Over an immense amount of time, a black hole will radiate away all its mass and evaporate completely. This leads to a profound problem called the black hole information paradox. What happens to the information about the things that fell into the black hole? According to quantum mechanics, information can never be truly destroyed. But if the black hole evaporates into a featureless bath of thermal radiation, the information seems to be lost forever. This violates a fundamental principle of quantum physics. The fuzzball proposal from string theory is one possible solution. If the information is stored in the strings that make up the fuzzball, it could be slowly released as the fuzzball evaporates, solving the paradox. Another, more radical idea is the firewall hypothesis. This suggests that the event horizon is not an empty, smooth place, but a wall of high-energy particles that would destroy anything trying to cross it. This would also preserve information, but it would violate Einstein's equivalence principle, which states that falling into a black hole should be an unremarkable experience. We may never be able to directly see inside a black hole, but by studying the gravitational waves emitted when black holes merge, scientists at LIGO and Virgo are starting to probe the nature of the event horizon. They are looking for echoes in the gravitational wave signal, which could be a sign of some exotic physics happening at the black hole's surface. These observations, combined with advances in theoretical physics, may one day give us an answer to one of the most profound questions in science: what lies at the heart of darkness. Number 10, is Newton's gravitational constant truly constant? The gravitational constant, known as big G, is one of the most fundamental numbers in physics. It appears in both Newton's law of universal gravitation and Einstein's equations of general relativity. It is the number that sets the strength of the gravitational force throughout the universe. But despite its importance, it is the least precisely known of all the fundamental constants. We know the mass of the electron to a precision of parts per million. We know the Planck constant to an even greater precision, but our measurements of G only agree to about a few parts in 10,000. This is not for lack of trying. Measuring G is notoriously difficult. Gravity is incredibly weak, so the gravitational force between any two objects in a laboratory is minuscule and easily swamped by other forces like tiny seismic vibrations or electrostatic charges. The first person to measure G was Henry Cavendish in 1798 in a famous experiment using a torsion balance. He measured the tiny gravitational attraction between two large lead balls and two smaller ones. Modern experiments use variations of this method, but they are still plagued by systematic errors that are hard to identify and eliminate. The frustrating thing is that different experiments, all meticulously performed by world-class teams, keep getting slightly different answers. One experiment will measure a value, and another, using a different technique, will measure a value that is statistically inconsistent with the first. The results are clustered around a value of about 6.674x 10 raised to the power of 11m raised to the power of 3 kg raised to the power of 1, 2, but the spread is much larger than the estimated errors of the individual experiments. This suggests that there might be some unknown source of error that is affecting all the measurements. This uncertainty has led some physicists to ask a more radical question: what if G is not constant? What if it changes over time or varies from place to place? This idea is not new. The physicist Paul Dirac proposed in the 1930s that G might be decreasing as the universe ages. His argument was based on a curious coincidence involving large numbers in physics. He noticed that the ratio of the electrical force to the gravitational force between an electron and a proton is a huge number, around 10 raised to the power of 39. The age of the universe, expressed in atomic units of time, is also a huge number of a similar magnitude. Dirac suggested this was not a coincidence and that the two numbers were related. For this to be true, the strength of gravity would have to decrease as the universe expands. This idea of a varying G has profound implications. If gravity were stronger in the past, it would change our understanding of the evolution of the universe, the formation of stars and galaxies, and the history of our own solar system. For example, a stronger gravity in the past would have made the sun burn brighter. This could have implications for the early climate of the Earth and the origin of life. Scientists have tried to test this by looking at various astronomical and geological records. They have used observations of distant supernovae, the cosmic microwave background, and the abundance of light elements created in the Big Bang to put limits on how much G could have changed over cosmic time. They have also used lunar laser ranging, where lasers are bounced off reflectors left on the moon by the Apollo astronauts to track the moon's orbit with incredible precision. Any change in G would cause a small change in the Earth-Moon distance. So far, all these tests have shown no evidence that G is changing. The constraints are very tight, suggesting that if G does vary, it does so by less than 1 part in a trillion per year. However, the discrepancy in the laboratory measurements remains a nagging puzzle. Could it be that G varies not with time, but with location or the density of surrounding matter? Or is there some other unknown physics at play? It is more likely that the problem lies in unidentified experimental errors. But until the measurements from different experiments converge on a single precise value, the possibility that we are misunderstanding something fundamental about gravity will remain. The quest to pin down the value of this universal constant continues, a reminder that even the most basic elements of our physical theories are still subject to scrutiny and revision. Number 9, does antimatter fall up or down? In 1928, the physicist Paul Dirac formulated a relativistic equation to describe the electron. His equation had two solutions, one for the familiar, negatively charged electron, and another for a particle with the exact same mass but a positive charge. This anti-electron, later named the positron, was the first predicted particle of antimatter. It was discovered in cosmic rays a few years later by Carl Anderson. We now know that every fundamental particle has an antimatter counterpart. When a particle and its antiparticle meet, they annihilate each other in a flash of energy. This raises a fascinating question. How does antimatter interact with gravity? Does an anti-apple fall from an anti-tree in the same way an apple falls from a tree? According to Einstein's theory of general relativity, gravity is a consequence of the curvature of space-time caused by mass and energy. The theory is built on the weak equivalence principle, which states that the trajectory of a particle in a gravitational field depends only on its initial position and velocity, not on its composition or internal structure. A feather and a cannonball fall at the same rate in a vacuum. This principle has been tested to incredible precision with normal matter. If it holds true, then antimatter, which has positive mass and positive energy, must fall down, just like normal matter. However, no one has ever actually performed the experiment. We have never dropped a piece of antimatter to see what happens. General relativity is a classical theory. It does not include quantum mechanics. It's possible that a full theory of quantum gravity could contain a surprise. Some alternative theories have proposed that antimatter could have anti-gravity, meaning it would be repelled by the gravitational field of normal matter. It would fall up. This would be a revolutionary discovery. It would mean that the weak equivalence principle is wrong, and general relativity would need to be modified. It could also have profound cosmological implications. For example, it might help explain why the universe appears to be made almost entirely of matter, with very little antimatter. According to the standard model of cosmology, the Big Bang should have produced equal amounts of matter and antimatter. They should have all annihilated each other, leaving behind a universe filled only with light. The fact that we exist means that there was a tiny asymmetry, a slight excess of matter over antimatter. The reason for this asymmetry is one of the biggest unsolved mysteries in physics. If antimatter has anti-gravity, it could have separated from matter in the early universe, forming its own galaxies and clusters far away from our own. So, how can we test this? The experiment is incredibly difficult. Antimatter is hard to produce and even harder to store. You have to create it in a particle accelerator and then trap it using strong magnetic and electric fields, because if it touches any normal matter, it will instantly annihilate. To measure the effect of gravity, you need to cool the antimatter particles down to extremely low temperatures to slow their random motion and then release them from the trap and see which way they fall. Several experiments at CERN in Geneva are trying to do just this. The Alpha-G experiment has succeeded in trapping atoms of antihydrogen and antiproton orbited by a positron in a vertical magnetic trap. By carefully controlling the magnetic fields, they can release the anti-atoms and see if more of them hit a detector at the top or the bottom of the apparatus. A similar experiment called GEBAR aims to create antihydrogen ions, cool them to ultra-low temperatures, and then measure their freefall in the Earth's gravitational field. Another experiment, AEGIS, will use a different technique to create a beam of antihydrogen atoms and measure its deflection as it travels through a gravitational field. These experiments are at the cutting edge of technology. They are pushing the limits of what is possible in trapping and manipulating antimatter. The first results are starting to come in, and so far they are consistent with antimatter falling down. But the measurements are not yet precise enough to rule out anti-gravity completely. A definitive answer is expected in the coming years. Whatever the result, it will be a landmark in our understanding of gravity and the fundamental nature of the universe. If antimatter falls down, it will be another triumph for Einstein's theory. If it falls up, it will open the door to a whole new world of physics. Number 8. Why does time seem to flow in only one direction? We experience time as a river flowing relentlessly from the past through the present and into the future. This is the arrow of time. But the fundamental laws of physics, including general relativity and quantum mechanics, are time symmetric. They work just as well forwards as they do backwards. If you were to watch a video of two billiard balls colliding, you wouldn't be able to tell if the video was being played forwards or in reverse. The laws of motion are reversible, so why is our universe so different? Why do we remember the past, but not the future? Why do eggs break but not unbreak? The standard answer comes from thermodynamics, specifically the second law of thermodynamics. This law states that the total entropy or disorder of a closed system always increases over time. The universe started in a very low entropy state at the Big Bang, a hot, dense, highly ordered soup of particles. Since then, it has been evolving towards a state of higher entropy. Stars burn out, structures decay, and the universe becomes more disordered. This increase in entropy is what gives time its direction. The arrow of time is the arrow of increasing entropy. But this just pushes the question back one step. Why was the entropy of the universe so low in the first place? This is a major puzzle in cosmology. The initial state of the universe seems to have been incredibly special and finely tuned. Yeah, if the Big Bang had produced a random high entropy state, the universe would be a boring, uniform gas with no stars, no galaxies, and no life. It would be in a state of thermal equilibrium with no arrow of time. The fact that we have a past, present, and future is a direct consequence of this mysterious low entropy beginning, where gravity plays a crucial role in this story. In most systems, entropy is associated with disorder and uniformity. A well-shuffled deck of cards has high entropy. A perfectly ordered new deck has low entropy. But with gravity, it's the other way around. A smooth, uniform cloud of gas has low entropy. As gravity pulls the gas together into clumps, forming stars and galaxies, the entropy of the system actually increases. This is because there are many more ways to arrange the particles in a clumpy state than in a uniform one. So the arrow of time, the increase of entropy is intimately linked to the clumping nature of gravity. And gravity is the engine that drives the formation of structure and the increase of disorder in the universe. Some physicists have wondered if the arrow of time could be linked more directly to the expansion of the universe. Perhaps time flows forward because the universe is expanding. This leads to an intriguing question. If the universe were to one day stop expanding and start contracting, would the arrow of time reverse? Would people start getting younger? Would broken eggs reassemble themselves? Most physicists think this is unlikely. The thermodynamic arrow of time would continue to point in the same direction, even in a collapsing universe. Entropy would continue to increase, but the connection between gravity, space-time, and the arrow of time is still not fully understood. Here, Roger Penrose has proposed a Weyl curvature hypothesis, which suggests that the initial state of the universe had a very specific geometric property related to its curvature, which accounts for its low entropy. Other more speculative ideas suggest that our universe could be part of a larger multiverse where time runs in different directions in different regions. For example, some models propose that the Big Bang was not a beginning, but a bounce from a previous contracting universe. In this scenario, there could be a universe on the other side of the Big Bang where the arrow of time runs backwards relative to ours. The mystery of time's arrow touches on the deepest questions about the nature of reality. It connects the large-scale structure of the cosmos with the small-scale quantum world and our everyday experience. We are so familiar with the flow of time that we take it for granted. But for a physicist, it is one of the most profound and persistent puzzles. It's a sign that our understanding of gravity, cosmology, and the fundamental laws of nature is still far from complete. Number 7. How did the first black holes form? In recent years, astronomers using telescopes like the James Webb Space Telescope have been discovering something impossible. They are finding supermassive black holes, millions or even billions of times the mass of our sun, in the very early universe just a few 100 million years after the Big Bang. These black holes are powering brilliant quasars that are shining from a time when the universe was just a toddler. The problem is, according to our standard theories, they shouldn't exist. There simply hasn't been enough time for them to grow so big. A standard black hole forms from the collapse of a massive star. When a star more than about 20 times the mass of the sun runs out of fuel, its core collapses under its own gravity, creating a stellar mass black hole, perhaps a few tens of times the mass of the sun. To grow into a supermassive black hole, this seed black hole would have to feed on a prodigious amount of gas, dust, and other stars. It would have to accrete matter at the maximum possible rate, known as the Eddington limit, continuously for hundreds of millions of years. Most models show that this process is too slow to explain the giant black holes we see in the early universe. It's like finding a fully grown redwood tree just a few days after planting a seed. This has led astronomers and physicists to search for new ways to form massive black holes quickly. One idea is the direct collapse black hole. In the early universe, before the first stars had formed and enriched the cosmos with heavy elements, there were giant clouds of pristine hydrogen and helium gas. In some of these clouds, conditions might have been just right to allow the cloud to collapse directly into a massive black hole, bypassing the star formation stage altogether. This could have created seed black holes that were already tens of thousands or even hundreds of thousands of times the mass of the sun. These quasi-stars would have had a much easier time growing into the behemoths we see today. Another possibility involves the very first generation of stars, known as population the third stars. These stars were forged from pure hydrogen and helium and are thought to have been incredibly massive, perhaps hundreds of times the mass of the sun. When these giants died, they would have left behind, black holes that were much larger than the ones formed from today's stars. In the dense star clusters of the early universe, these black holes could have quickly merged with each other, building up to intermediate mass black holes and then eventually supermassive black holes. A more exotic idea is that the first black holes were not formed from collapsing matter at all. They could be primordial black holes formed in the first second after the Big Bang. In the incredibly dense and chaotic early universe, small fluctuations in density could have been so extreme that some regions collapsed directly into black holes under their own gravity. These primordial black holes could have come in a wide range of sizes, from smaller than an atom to many thousands of times the mass of the sun. If they existed, they could be the seeds of the supermassive black holes we see. They could also be a candidate for dark matter. However, we have no direct evidence that primordial black holes were ever formed, and astronomical observations have placed tight constraints on how many of them could be out there. The discovery of these early, oversized black holes is a major challenge to our understanding of cosmology and galaxy formation. It seems that the universe was able to assemble its largest structures much more quickly and efficiently than we thought. Gravity is at the heart of this process. Understanding how these first black holes formed will require a better understanding of how gravity operates in the extreme environments of the early universe and how it interacts with gas dynamics and the formation of the first stars. The James Webb Space Telescope is continuing to push our view of the cosmos further back in time, and each new discovery of an ancient quasar adds another piece to this fascinating puzzle. Number 6. What happens to information that falls into a black hole? The black hole information paradox is one of the most profound and difficult problems in theoretical physics. It pits our two most successful theories, general relativity and quantum mechanics, against each other in a fight to the death. The problem was first identified by Stephen Hawking in the mid-1970s. He discovered that, due to quantum effects, black holes are not completely black. They emit a faint thermal radiation, now called Hawking radiation. This means that black holes have a temperature, and that they slowly lose mass over time. Over an unimaginably long period, a black hole will completely evaporate, leaving nothing behind but a featureless cloud of this radiation. Here is the paradox. According to the no-hair theorem of general relativity, a black hole is a very simple object. It can be completely described by just three properties: its mass, its spin, and its electric charge. It has no hair, meaning no other features. This means that if you make a black hole by collapsing a star, or by throwing in a set of encyclopedias, the final state of the black hole is the same as long as the mass, spin, and charge are the same. All the detailed information about what made the black hole, the chemical composition of the star, the words in the encyclopedias is lost behind the event horizon. This is not a problem as long as the black hole is stable. You can just say the information is still inside, hidden from view. But what happens when the black hole evaporates? The Hawking radiation it emits is thermal, meaning it is random and carries no information about what fell in. So, when the black hole is gone, the information seems to be gone with it forever. This violates one of the most fundamental principles of quantum mechanics, the principle of unitarity. This principle states that information can never be created or destroyed. The total amount of information in the universe must be conserved. The evolution of a quantum system must be reversible. If you know the final state, you can, in principle, calculate the initial state. But if information is destroyed in a black hole, this is no longer true. This is a deep crisis. Either general relativity is wrong, or quantum mechanics is wrong, or they are both incomplete in some fundamental way. As physicists have been struggling with this paradox for nearly 50 years, and there is still no consensus on the solution. One of the earliest proposals from Hawking himself was that information is simply lost. This would mean that quantum mechanics needs to be modified. This is a very radical step that most physicists are unwilling to take, because quantum mechanics has been tested so thoroughly. Another idea is that the information is not lost, but is somehow encoded in the outgoing Hawking radiation. The radiation would not be perfectly thermal, but would contain subtle correlations that carry the information. The problem with this idea is that it's not clear how the information gets out from behind the event horizon. It would seem to require information to travel faster than light. A third possibility is that the information is left behind in a remnant. As the black hole evaporates, it might not disappear completely, but leave behind a tiny, stable, Planck mass object that contains all the information. The problem here is that you would need an infinite number of different types of remnants to store the information from all the possible things that could have formed a black hole. More recent ideas have come from string theory and the holographic principle. The fuzzball proposal suggests that black holes are not singular objects with a sharp event horizon, but are extended, stringy objects. The information is stored in the specific configuration of the strings, and it is never truly lost. Another idea related to the ADAS-CFT correspondence is that the information is stored on the event horizon itself and is projected into the surrounding spacetime. This has led to some very strange ideas, like the ER equals CPR conjecture, which proposes that the entanglement between two quantum particles is connected by a tiny wormhole in Einstein-Rosen bridge, or ER. This suggests a deep connection between the geometry of spacetime and the quantum information it contains. The information paradox is not just a theoretical curiosity, it is a signpost pointing towards the next revolution in physics. The solution, whatever it may be, will require a true theory of quantum gravity. It will force us to rethink our most basic concepts of space, time, information, and reality itself. Number 5, are there extra dimensions of space? We live in a world with 3 spatial dimensions: length, width, and height, and 1 time dimension. But what if this is not the whole story? What if there are other hidden spatial dimensions that we cannot perceive? This might sound like science fiction, but it is a serious idea that has been a part of theoretical physics for over a century. The first person to propose an extra dimension was the Polish mathematician Theodor Kaluza in 1919. He was trying to unify Einstein's new theory of gravity with James Clerk Maxwell's theory of electromagnetism. He discovered that if he wrote down Einstein's equations for a universe with 4 spatial dimensions instead of 3, something remarkable happened. The equations naturally split into 2 sets. One set was the familiar equations of general relativity in 3 dimensions. The other set was Maxwell's equations for the electromagnetic field. This suggested that gravity and electromagnetism could be two different aspects of a single force, geometry, in a higher dimensional spacetime. But if this extra dimension exists, where is it? The Swedish physicist Oskar Klein suggested in 1926 that the extra dimension is not large and extended like the ones we know. Instead, it is curled up into a tiny circle at every point in our space. It would be so small, on the order of the Planck length, that we would never be able to see it or move in it. It's like a garden hose. From far away, it looks like a one-dimensional line, but if you look closely, you see that it has a second circular dimension. In this Kaluza-Klein theory, particles like the electron would be moving in tiny circles in this extra dimension, and this motion is what we perceive as electric charge. The idea of extra dimensions was revived in the 1980s and 1990s with the advent of string theory. String theory requires not just one, but 6 or 7 extra spatial dimensions for its mathematical consistency. In this theory, the fundamental particles are not points, but tiny vibrating strings. The way a string vibrates determines what kind of particle it appears to be. An electron is a string vibrating in one pattern, a photon is a string vibrating in another. The geometry of these extra curled-up dimensions, known as a Calabi-Yau manifold, determines the properties of the particles and the forces in our universe. It dictates the constants of nature. More recently, a different kind of extra dimension theory has been proposed, known as the brane world scenario. In this model, the extra dimensions don't have to be small. They could be large, even infinite. Our universe, with all its particles and non-gravitational forces, would be confined to a 3-dimensional brane embedded in a higher dimensional space called the bulk. Only gravity and perhaps some other exotic particles would be able to travel in the bulk. This could explain why gravity is so much weaker than the other forces, the hierarchy problem. Gravity's strength would be diluted because it is spreading out into these extra dimensions. How could we test for the existence of extra dimensions? If the extra dimensions are large enough, we might be able to detect their effects at particle accelerators like the Large Hadron Collider. High-energy collisions could create particles that travel off into the extra dimensions. These particles would be invisible to our detectors, but they would carry away energy and momentum, leaving a characteristic signature of missing energy. So far, no such signal has been seen. Another way is to look for tiny deviations from Newton's law of gravity at very short distances. If there are extra dimensions, gravity should become stronger at scales comparable to the size of those dimensions. Precision experiments are probing gravity at the sub-millimeter level, but have not yet found any deviation. The existence of extra dimensions would fundamentally change our view of the cosmos. Our universe would be just a slice of a much larger, more complex reality. It's a mind-bending idea and one that is still purely theoretical. But it is a powerful one, offering potential solutions to some of the deepest mysteries in physics, from the weakness of gravity to the nature of dark matter. The search for these hidden worlds continues, pushing the boundaries of both experimental and theoretical science. Number 4, did the universe have a beginning? The standard model of cosmology, the Big Bang Theory, describes a universe that began about 13.8 billion years ago from an incredibly hot, dense state. All the space-time, matter, and energy in the universe was contained in a single point, a singularity. From this point, the universe has been expanding and cooling ever since. This model is supported by a wealth of evidence, including the observed expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements. But the idea of a beginning, a moment of creation out of nothing, is a difficult one, both philosophically and physically. The singularity at the start of the Big Bang is like the singularity inside a black hole, a point where our current laws of physics break down. General relativity cannot describe what happens at that point. It is a boundary to our knowledge. This has led many physicists and cosmologists to question whether the Big Bang was truly the beginning of everything. Perhaps it was not a creation, but a transition from a previous state. One of the most popular alternatives is the idea of a big bounce. In this model, our universe is part of a cyclical process of expansion and contraction. The Big Bang was preceded by a contracting universe which collapsed down to a very high density and then bounced, re-emerging as our expanding universe. This avoids the singularity. The bounce would be governed by the laws of quantum gravity, which would take over at extreme densities and prevent a complete collapse. The loop quantum gravity, for example, naturally predicts such a bounce. The theory's discrete space-time structure provides a kind of quantum pressure that resists the crush of gravity. Another idea is the ekpyrotic or cyclic model, which comes from string theory and the idea of branes in extra dimensions. In this scenario, our universe is a three-dimensional brane. The Big Bang was caused by the collision of our brane with another brane in a higher dimensional space. These collisions would happen periodically, leading to an endless cycle of creation and destruction. Each collision would heat up our brane, creating the hot, dense state we call the Big Bang, and triggering a new phase of expansion. There is also the idea of an eternal, inflating multiverse. According to the theory of cosmic inflation, the very early universe underwent a period of hyper-fast exponential expansion. In many models of inflation, once it starts, it never completely stops. It ends in some regions of space, creating pocket universes like our own, but it continues in the space between them. This process, called eternal inflation, would create an infinite number of universes, each with potentially different physical laws and constants. In this picture, our Big Bang was not the beginning of everything, but just the moment when inflation ended in our particular patch of the multiverse. The multiverse as a whole would have no beginning and no end. Can we ever find out what happened before the Big Bang? It might seem impossible, since any information from a previous era would have been scrambled by the extreme conditions of the Big Bang itself. But there might be some faint whispers from a pre-Big Bang epoch left in the sky. Some cyclic models predict specific patterns of gravitational waves that could be imprinted on the cosmic microwave background. The discovery of such a signal would be revolutionary. Another approach is to look for theoretical consistency. A successful theory of quantum gravity should be able to describe the Big Bang singularity and tell us whether it was a true beginning or just a phase transition. The question of origins is one of the most fundamental that we can ask. Was our universe a singular event, a unique creation? Or is it just one chapter in an eternal cosmic story? The answer lies hidden in the moment of the Big Bang, a moment where gravity was so strong that space and time themselves were forged. To understand our beginning, we must first understand the true quantum nature of gravity. Number 3 is our universe a hologram. The idea that our universe might be a hologram is one of the strangest and most powerful ideas in modern physics. It suggests that the three-dimensional world we experience is an illusion, a projection of information stored on a two-dimensional surface at the edge of the universe. This is not a metaphor, it is a precise mathematical conjecture about the nature of space, time, and gravity. The holographic principle grew out of the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something very strange about the entropy of a black hole. Entropy is a measure of the amount of information a system can hold. They found that the entropy of a black hole is not proportional to its volume, as you might expect. It is proportional to the surface area of its event horizon. This was a shocking result. It's as if all the information about the three-dimensional objects that fell into the black hole is somehow stored on its two-dimensional surface. This led the physicists Gerard and Hooft and Leonard Susskind to propose the holographic principle in the 1990s. They suggested that this property might not just be true for black holes, but for any region of space. The maximum amount of information that can be contained in a volume of space is determined not by the volume itself, but by the area of its boundary. This is deeply counterintuitive. It's like saying that the amount of information you can store in a warehouse depends on the square footage of its walls, not its total cubic footage. If this principle is correct, it means that our three-dimensional reality might be fundamentally redundant. All the information needed to describe our universe could be encoded on a distant, two-dimensional surface. We would be the hologram projected from this surface. This idea was given a solid mathematical footing in 1997 by the physicist Juan Maldacena. He discovered a precise mathematical duality, now called the ADS-CFT correspondence. He showed that a theory of gravity, specifically string theory in a certain kind of five-dimensional, saddle-shaped spacetime called anti-de Sitter space ADS, is mathematically equivalent to a quantum field theory without gravity, a conformal field theory, or CFT, living on the four-dimensional boundary of that space. The two theories look completely different. One includes gravity and lives in 5 dimensions. The other has no gravity and lives in 4 dimensions, but they are mathematically interchangeable. They are two different descriptions of the same underlying reality. You can translate any question from one theory into the other, solve it, and translate it back. This correspondence is the most concrete realization of the holographic principle we have. It provides a way to study quantum gravity by using the tools of a much simpler, non-gravitational quantum theory. It has become one of the most important and fruitful ideas in theoretical physics, with applications in fields ranging from black hole physics to condensed matter physics. But our universe is not an anti-de Sitter space. It is expanding and has a different geometry. So does the holographic principle apply to our universe? We don't know for sure, but many physicists believe that some version of it must be true. It offers a potential solution to the black hole information paradox. If the information is stored on the boundary, it is never truly lost. It also suggests that space-time itself is not fundamental, but is an emergent property of the underlying quantum information. How could we ever test such a bizarre idea? One possibility is to look for signs of holographic noise. If our 3D world is a projection from a 2D surface made of tiny, Planck-sized bits, then there might be a fundamental limit to the precision with which we can measure positions in space. This would manifest as a tiny, random jitter in the positions of objects, a kind of cosmic fuzziness. An experiment at Fermilab called the holometer was designed to look for this noise by using a powerful laser interferometer. The experiment did not find the expected signal, ruling out some simple holographic models, but the principle itself remains a powerful and compelling idea. The holographic principle challenges our most basic intuitions about reality. It suggests that the world we see is a shadow, a projection of a deeper reality taking place on a distant screen. It blurs the line between geometry and information, and it may hold the key to a final theory of quantum gravity. Number 2, what is the ultimate fate of the universe? The fate of the universe is inextricably linked to the nature of gravity and the mysterious substance called dark energy. For most of the 20th century, there were 2 main possibilities. If there was enough matter in the universe, its collective gravity would eventually halt the cosmic expansion and pull everything back together in a fiery big crunch, a sort of Big Bang in reverse. If there wasn't enough matter, gravity would not be strong enough to stop the expansion, and the universe would expand forever, growing colder, darker, and emptier in a scenario called the Big Freeze or heat death. Then, in 1998, came the discovery that the expansion of the universe is accelerating. This changed everything. This acceleration is driven by dark energy, a repulsive force that is pushing the cosmos apart. The ultimate fate of the universe now depends on the nature of this dark energy. Is it a constant, or does it change over time? If dark energy is a cosmological constant, as Einstein first proposed, then its energy density is constant. As the universe expands, the density of matter and radiation decreases, but the density of dark energy remains the same. This means that dark energy becomes more and more dominant over time. In this scenario, the universe will expand forever at an ever-increasing rate. Galaxies will be pushed apart from each other faster and faster. In about 100 billion years, all galaxies outside our own local group will have receded beyond our cosmic horizon. The night sky will become dark and empty. Over trillions of years, the stars in our own galaxy will burn out. The galaxy will slowly disintegrate, its dead stars and planets either falling into the central black hole or being flung out into the void. The black holes themselves will eventually evaporate through Hawking radiation. The universe will end as a cold, dark, and empty place, a thin soup of elementary particles and low-energy photons, approaching a state of maximum entropy. This is the big freeze. But what if dark energy is not constant? What if its strength increases over time? This is the idea of quintessence, a dynamic form of dark energy. If the repulsive force of dark energy grows stronger and stronger, it could lead to a much more dramatic end. In this scenario, called the Big Rip, the accelerating expansion would become so powerful that it would overcome not just the gravity between galaxies, but all the forces that hold things together. First, it would tear apart galaxy clusters, then it would strip galaxies of their stars. In the final moments, it would overcome the gravitational pull of stars, ripping planets from their orbits. Then it would overcome the electromagnetic forces that hold atoms together, and finally, the strong nuclear force that holds atomic nuclei together. In the last fraction of a second, space-time itself would be torn apart. Everything in the universe would be shredded into its fundamental constituents. There is also a third possibility. What if the dark energy is not permanent? What if it is a temporary field that could one day decay? If dark energy were to disappear, or even change from a repulsive force to an attractive one, gravity can once again become the dominant force in the cosmos. The expansion could slow, stop, and reverse, leading to the big crunch that was once the leading theory. The universe would collapse back in on itself, ending in a singularity, possibly triggering a new Big Bang in a cyclical universe. Which of these fates awaits us? The answer depends on a single number, the equation of state parameter of dark energy, usually denoted by the letter W. This number describes the ratio of the pressure of dark energy to its energy density. For a cosmological constant, W is exactly 1. If W is greater than 1, the universe will end in a big freeze. If W is less than 1, a scenario known as phantom energy, it will end in a big rip. Recurrent measurements from telescopes studying supernovae and the large-scale structure of the universe show that W is very close to 1. The data is consistent with a cosmological constant, but there is still some uncertainty. Future observatories like the Vera C. Rubin Observatory and the Euclid Space Telescope will measure the expansion history of the universe with much greater precision. They will be able to track how W has changed over cosmic time. These measurements will tell us whether dark energy is truly constant or if it is evolving. By doing so, they will give us a glimpse into the distant future and tell us how the cosmic story will end. It is a story written by gravity and dark energy, a cosmic battle between attraction and repulsion that will determine the ultimate destiny of everything. Number 1, what is gravity? After all this, we are left with the most fundamental question of all. What is gravity? We can describe what it does with incredible precision. We know that it is a force that pulls objects with mass and energy towards each other. We know that it governs the orbits of planets, the formation of stars, and the expansion of the universe. We have Einstein's theory of general relativity, which describes gravity as the curvature of space-time. This theory is one of the most successful scientific theories of all time, passing every experimental test we have thrown at it. But describing what gravity does is not the same as understanding what it is. General relativity tells us that mass curves spacetime, and spacetime tells mass how to move. But it doesn't tell us why. Why does mass have this intimate relationship with the geometry of the universe? What is the underlying mechanism? The theory is silent on this point. It is a classical theory. It does not incorporate the principles of quantum mechanics. We know that the other three forces of nature are quantum forces mediated by the exchange of particles. It seems almost certain that gravity must also have a quantum description, but we don't have one. The search for a quantum theory of gravity is the most important and most difficult problem in fundamental physics. It is the quest for a theory of everything that would unite general relativity and quantum mechanics into a single coherent framework. There are two main approaches. The first is string theory, which proposes that the fundamental constituents of the universe are not point particles, but tiny vibrating strings. One of the vibrational modes of these strings corresponds to a particle with the properties of the graviton, the hypothetical quantum of gravity. In this view, gravity is not a property of space-time itself, but a consequence of the interactions of these fundamental strings. Space-time itself is an emergent phenomenon. The second major approach is loop quantum gravity. This theory takes the opposite approach. It starts with the principles of general relativity and tries to quantize spacetime itself. In LQG, space is not a smooth continuum, but a granular network of discrete quantum loops. Time flows in discrete ticks. Gravity is the geometry of this quantum network. It is not a force that propagates through spacetime. It is the fabric of spacetime. These two theories offer radically different pictures of what gravity is at the fundamental level. And there are other, more speculative ideas like the theory of emergent gravity, which suggests that gravity is not a fundamental force at all, but a thermodynamic or entropic effect, a statistical consequence of the quantum information that underlies our universe. The problem is that we have no way to test these theories. The energy scale at which quantum gravity effects would become important, the Planck scale, is about 16 orders of magnitude higher than the energies we can reach at the Large Hadron Collider. It is so far beyond our experimental reach that direct tests are almost impossible. So physicists must look for indirect clues. They look for tiny inconsistencies in our current theories, for puzzles and paradoxes like dark energy or the information paradox. They look for subtle signatures in the cosmic microwave background or in the gravitational waves from black hole mergers. Gravity was the first of the fundamental forces to be discovered, yet it is the last to be understood. It is the familiar force that keeps our feet on the ground and the cosmic architect that shapes the universe. It is the weakest of all the forces, yet it holds the key to the deepest mysteries of space, time, and the cosmos. We have learned so much since Newton watched the apple fall. We have learned that gravity can bend light, slow time, and create ripples in the fabric of reality. But we still do not know what it is. The quest to answer this simple question is the ultimate frontier of human knowledge.